We're now going to start working with obtuse angles or angles larger than 180 degrees. In fact, we can work with crazy revolutions around a circle, because if we know the trig for acute angles, basically we know the trig in quadrant 1, we can apply that knowledge to any quadrant using the idea of reference angles. If you were in my AP Pre-Cal class last year, I never used the actual phrase reference angle, but what we would do around the unit circle is think, well, if this one is pi divided by 6, then 5 pi divided by 6 would be about the same. It's the same concept of reference angles. We're looking for angles or lines around our unit circle that would use the same measurement. A reference angle is kind of like the little bow tie that is created by each of these angles in each quadrant. So if I look right here in quadrant 1, the reference angle and the regular angle are the exact same thing. So I'm going to color in right here. We've made a right triangle with our actual angle. That's normal. That's what we did last time. If we move into quadrant 2, so our angle theta takes us all the way to the terminal ray being right here. Instead of doing trig with this obtuse angle, what I'm going to use is the reference angle, basically that makes a right triangle for me going down towards that x-axis. If theta goes all the way to quadrant 3, so here's 0, we're all the way right here, I again want to make a right triangle with the x-axis, so my reference angle is going to be right here, going back towards the x-axis. And likewise, all the way in quadrant 4, if we whip all the way around to quadrant 4, my reference angle still creates that right triangle, an acute right triangle, in quadrant 4. I call these the bow tie reference angles because if I put them all together on one, which would never happen, but imagine like in the center here, we have the reference angle in quadrant 1, the reference angle in quadrant 2, reference angle in quadrant 3, and reference angle in quadrant 4. It kind of looks like a bow tie to me. So as long as you are making a bow tie with the angles that you are using, basically going towards the x-axis, whether that's up or down, you are using the reference angle for that larger angle. Okay, let's just start there and make sure we know how to find these reference angles. We're going to sketch the angle and then find the reference angle for each angle. To sketch an angle, you just draw like a plane x and y axis, and you then show me where this angle would be. Now, 218 degrees, what quadrant would that be in? Quadrant 3, because it would end somewhere over here. So my angle, well, pow, looks something like this. Here's theta equal to 218 degrees. What I want, though, is not the entire angle, because I don't want to do trig with obtuse angles. I actually want to do trig with acute angles, since we already know that. So what we do instead is we look at this angle right here. This becomes our reference angle. Now, if the flat line is 180 degrees, and the angle we drew is 218 degrees, what is our reference angle? 38 degrees. How did you get that?
218 minus 180.
Yeah, 218 minus 180. We're taking away quadrants 1 and 2 basically, and seeing what would be left over to finish making this crazy large angle. So our reference angle, which our book displays as theta with a little apostrophe next to it, theta prime would be the way I'd want to say that. I've also, if you look things up online, have seen it written as a subscript of ref, theta reference, it's your reference angle. Either will work for me, but I'm pretty sure your textbook uses the theta prime, or the theta with the little tick mark next to it. That is your reference angle. Later on today, that's the angle we're actually going to do trig with, instead of the larger angle. We'll get there. Yes? How did we get that again? Great question. Thank you for asking. If I start here, this is 0? 90, 180. How much more did I need to go to get to 218? I needed to go 38 more. So my reference angle is 38.
So 180 minus 218 minus 38.
Correct. Yeah. And it's not always 218 minus 38. It's that in quadrant 3. I like to think of it, how much less or how much more did I need to go before I'm on one of the flat x-axis, axes. Okay. What about this crazy large angle? Let's sketch 1,387 degrees.
Oh, joy.
I know. It'll be fun.
No.
Okay, here's my x and y axis. Let's just make this easy for ourselves. This is 0 degrees. If I go all the way around, how much is that also?
360.
What if I went around again? And what if I went around again?
1080.
1080. What if I went around one more time? 1440.
Because you just did it.
So I can loop around this circle 5 times. So 360, 720, 1080, 1440. And here's what my angle is going to look like. Boom, 2, 3, 4. Whew, but I don't want to finish the whole thing, right? Because I didn't quite make it to 1440 if I'm at 1387. So instead, I'm going to end my terminal ray here. Do we need to see me do that again?
Wait, 4 or on the 5? What?
I'll do it again. I'll do it again. Do you loop too many? You loop too many times? Okay. 360,
Yeah.
720,
Yeah.
1080. I don't want to go all the way to 440, so I'm going to stop here. So 4, almost 5. 360, 720, 1080. Oh, wait, no, 3, almost 4. You were right.
Oh, okay, I was like, wait.
I swear I can count 5 numbers, but the first one was 0. Okay, question. We need the reference angle because this large, crazy large angle is 1,387, and I really don't want to do trig with that large of a number. So instead, what we can use is we can use the reference angle that's left over to basically finish that last full loop, that last full revolution. What is my reference angle? 53 degrees. How did we get 53 degrees?
1440 minus 13.
Yeah, if we know this ends at 1387, how much more did I need to go to make it all the way to 1440? I needed 53 more degrees. So it's 1440 minus 1387. Questions, comments, concerns?
Is this it?
Are we gonna have to go higher?
Maybe,
Miss?
Like in this one?
maybe.
Miss?
I'm not saying I can't, it won't not happen, but I'm not gonna be like it's happening. So let's see, why do we do this? Why do we use reference angles? Great question. So glad you asked why we use reference angles. Here's what we want to do is we want to find the exact values of the 6 trig functions. That's a question I asked you last class, but we're doing this with 210 degrees. This is a large angle, an angle outside of quadrant 1. So instead of doing the sine of 210 degrees, which yes, your calculator could answer for you, what we want to do is think about the reference angle that we are using. I've already sketched 210 degrees for you and given you a good hint on what your reference angle is. So if 210 is in quadrant 3, what's this reference angle? 30. So my reference angle is 30 degrees. Instead of doing sine of 210, we can honestly just do sine of 30. Except for we have to check whether it's going to be positive or negative. So do y'all remember back from, did I do that in this class? All of my classes are learning the same thing at different times. I can't keep it straight. Did we do all-star trig class?
Yes.
Okay, great. I'm going to list that right here. If we're in quadrant 3, which we are in quadrant 3, which of my trig functions should be positive? Tangent and cotangent, which means literally everything else needs to be the negative version of its quadrant 1. So sine of 210 degrees is just like doing the sine of 30 degrees. Flip back to that table I told you was important from the last section. What is the sine of 30 degrees? 1/2, but since we're in quadrant 3, we're going to make it negative 1/2. That is the sine of 210 degrees. We can instead use the reference angle as long as we remember which quadrant we're in. Okay, in my regular pre-cal class, I was writing this down, and I'm not going to have you guys write it, but sine of 210 degrees is the same thing as the sine of 30 degrees, but in quadrant 3. That's what that looks like a 2. Let me fix. That looks like the same thing because sine of 30 degrees is 1/2, but in quadrant 3, we have to pop the negative on a sign. So I don't need to see all of this work, but that's what I'm doing each time. Just FYI, this is like the thought process, which means now if I was doing the cosine of 210, I'm basically doing the cosine of 30. Based on that table, what is the cosine of 30 degrees? Which number specifically?
Negative number.
It is negative, right?
Wait, say again, cosine of 30?
Cosine of 30.
It's square root of 3 over 2.
Very good. So we can just think about cosine of 30, except that we know it's in quadrant 3, so we have to make it negative. Last one, if you're still looking at that table, what is the tangent of 30 degrees?
Positive.
It will be positive because we're in quadrant 3. Very good. But the actual number for tangent of 30?
Square root of 3 over 3.
Square root of 3 over 3. We're not going to have time to finish the reciprocals. Oh, because there's the bell for lunch, but we'll finish it after lunch. Right before lunch, we had just finished sine, cosine, and tangent. Remember what we did? Saw that, Michaela.
I'm sorry.
What we did was we thought sine of 210, but we used the reference angle. We used 30 instead of 210. Except knowing that it's in quadrant 3, we knew we were going to make sine and cosine negative. Now, of course, doing cosecant and secant, all we have to do is flip the value we have for sine of 210 for cosecant, which means this is negative 2. We flip the value for 210 of cosine, which would be negative 2 square root of 3 over 3, once we rationalize that denominator. And then cotangent of 210 degrees will be positive square root 3, because it would be 3 square root 3 over 3, and the 3's cancel. So again, once we find a value we know in quadrant 1, once we know the reference angle, it will be an angle in quadrant 1 because it's always going to be an acute angle. And so we can do trig outside of quadrant 1. These steps that we just did is exactly what's summarized in the main idea box right here in case you forgot what we did. But we're going to go ahead and jump to example 3. That wants us to find the exact value of cosine of negative 240. So now we're going to put the two pieces together. We need to start by sketching the angle so we can find the reference angle, and then we'll do the trig with that acute angle. So let's draw negative 240 degrees. Oof, since it's negative, which direction around this axis are we going?
Clockwise.
Clockwise. Where would 240 be by going clockwise? Quadrant 1, 2, 3, or 4?
3.
So you don't reorder the quadrants, shall I say. It's still quadrant 1, 2, 3, 4.
2.
It will be in quadrant 2 because it's going to be more than negative 180. So that means we're going to be here in quadrant 2. I'm going to redraw this graph because that looks horrible. So here's negative 240 degrees. You're welcome. Okay. Once we know where theta is, where the terminal ray lies, we need to find the reference angle. Remember, we're always going towards the x-axis like a bow tie. Don't draw my reference angle towards the y-axis. It's always towards the x. Now, if the full angle is negative 240, how much is that blue reference angle? 60. The blue reference angle would be 60 degrees. That's my reference that we're going to use. So really, the cosine of negative 240 is exactly like saying, cosine of negative 240 is exactly like doing the cosine of 60 degrees, but we're in quadrant 2. So question, in quadrant 2, is cosine positive or negative? Negative. And then what is the cosine of 60 degrees? This is where you refer to that table.
What table?
From the end of 2.1, cosine of 60 degrees.
Wait, are we looking for the cosine right now?
Yes. Should be 1/2, yes? So the answer for cosine of negative 240, which is the same as cosine of 60, but put it in quadrant 2, will be negative 1/2. So we need to know where the angle is so we can find the reference angle, do trig with that acute reference angle, and then make sure we give it the right positivity based on the quadrant it's in. Can we try tangent of 650? I mean 675. I can read.
Oh, joy.
Where is 675? That's the first step.
It's on the coordinate plane.
Yes, it's definitely going to be well, it's going to be more than one lap around, yes? So let's do those numbers from the laps again. We start with 0 and then one full lap.
So quadrant 1.
And if we do a whole nother one, it's 720. So we didn't make it all the way to 720, but we did make it back into quadrant 4. So this angle's going to look like this. Kapow. Somewhere in quadrant 4. We need to know what that reference angle would be, though.
It's the number.
So how many degrees is it from 675 to 720? How about 675 to 700? 25, and then what, 700 to 720?
45.
Okay, so we're at 45. So we know that our reference angle is 45 degrees. So the tangent of 675 degrees is like the tangent of 45 degrees, but we are in quadrant 4. So in quadrant 4, is tangent positive or negative? Negative. And what is the tangent of 45 degrees? 1. So the tangent of 675 degrees is 1.
Why is negative?
It's negative because in quadrant 4, tangent is negative. That's the C quadrant. All-Star Trig class. Now this kind of problem can now become a part of a bigger problem. So what if we use these special angles and I wanted you to evaluate the following? I want you to give me the number that cosine of 120 degrees plus 2 times sine squared of 60 degrees minus tangent squared of 30 degrees is.
It may sound like this.
It'll be fine. Don't panic. The only angle that is larger than 90 degrees in this problem is the 120. So the only thing we need to think about that's difficult here is where 120 is. And what quadrant is 120? Quadrant 2. So if this is 120 degrees, what's my reference angle? 60. It takes 60 more degrees to finish out that entire flat line. So that means that our reference angle here is 60. So instead of doing cosine of 120, I can do the cosine of 60 degrees as long as I remember it's in quadrant 2. What is the cosine of 60 degrees? Look at that table.
1/2.
1/2. In quadrant 2, is cosine going to be positive or negative?
Negative.
Negative. So we know that the first little bit, cosine of 120, is negative 1/2. While you're still looking at that table, what is the sine of 60 degrees? What is the sine of 60 degrees?
Square root 3 over 2.
Okay, while you're still looking at that table, what is the tangent of 30 degrees?
Square root 3 over 3.
Square root 3 over 3. So because 60 and 30, one are from my special right triangles, and they're acute angles, they're in that table. So we know these values. So I can substitute all this stuff back in. If I take this equation and I rewrite it now with the values we know for each of them, it would be cosine of 120, which is 1/2, plus 2 times the sine of 60 squared. Sine of squared of 60. That's technically how you say it. Minus tangent of 30, quantity, squared. Do we see how I'm substituting these in? The only one we had to do anything beyond quadrant 1 was that first one. Otherwise, we're just reading off the table. It's arithmetic now. What's square root of 3 over 2 squared?
A number?
3 over 4. How did it become 3 over 4? We square the top. What is square root of 3 squared? And what is 2 squared? 4. So really, this is going to start simplifying down to negative 1/2 plus 2 times the square root of 3 over 4. Just kidding. That literally, we just discussed how that went away. Come on, Miss Quigley. Minus, what is square root of 3 over 3 squared?
3 over 9, which is 1 over 3.
3 over 9, which, yes, reduces to 1/3. We'll go ahead and do that since you see it. We can also reduce that middle bit, right? What's 2 times 3 over 4?
6, 8, 7, 1/2. Wait,
1 over 3. I don't remember.
Okay,
Or is it 2 over 3?
so 2 times 3 is 6. 6 over 4 reduces to
2.
3 over
3 over 4, right?
2.
Yeah.
Also known as, you can take a 2 out of here and this cancels, makes 2.
Oh. So it's just 3 really?
It's just 3 over 2. We worked really hard there. Okay, problem. The reason I'm showing all of this work is because some of us may be retaking our SATs soon. And I know at this point, SATs, you still get a calculator. Some of us may be retaking our TSIs. You don't always get a calculator on your TSIs. We do want to review just for a second. How do you add all of these fractions together? What's the rule for fractions? What do they need to have? Common denominator. Right now my denominators are 2, 2, and 3. What's the least common denominator between them?
2. No, 6.
Least common multiply, I guess, which would make the least common denominator, should be 6. So negative 1/2, I can change to negative 3 over 6, because that's the same thing. 3 over 2, I can change to 9 over 6, because 2 times 3 is 6, so 3 times 3 is 9. And then 1/3, what would I change that to? 2 over 6. So then once they have the same denominators, you just do the arithmetic with the top. Negative 3 plus 9 is 6. Minus 2 is 4. So 2/3. Good little arithmetic review. To add and subtract fractions, they have to have a common denominator. Yes? Yes. Like originally, yeah. You totally could have. I just didn't think about it. But yeah, that totally works. Okay, so this little bit, the little bit we did up here, changing cosine of 120 to an acute angle using its reference angle, is kind of like the gist of today, being able to do trig outside of quadrant 1. So let's make some maybe some easier things to do here instead of sketching those graphs where we had to like loop around a crazy number of times, because even I miscounted the number of loops I did. Instead of doing tons of loops, let's just use coterminal angles. So remember in the first chapter when we learned about coterminal angles, it was just multiples of 360 added or subtracted away from it. So if I wanted to change cosine of 780 to an angle that was within 0 and 360 degrees, all I'd have to do is subtract 360 from 780. What is 780 minus 360? 420. So if I subtract that, this is the same as the cosine of 420 degrees. Still too big. Subtract 360 again.
80, right?
60? Right? Yeah. This is exactly what we would get as our reference angle if we drew 780 and looped it around a few times. We'd have a reference angle of 60. This is the same concept. This is why reference angles work. So cosine of 60, that's something from my table. That's 1/2. The end, I'm done.
So you told us the hardest way to do it.
Well, I'm going to ask you to sketch angles, so you do need to know how to do that. We need to know where angles lie, but if you can see that there are revolutions around 360, you can just take that away to make it an easier angle to work with. Or let's say we're doing cotangent of negative 405. This time, instead of subtracting 360, I'm going to add 360 because I want to make it a positive number. Negative 405 plus 360 is negative 45 degrees. Still negative. Don't love that for myself. So we're going to add 360 again, and we end up getting the cotangent of 315. Yikes. That's a really large angle. But what do you think the reference angle is going to be here? 45. Because if we thought about 360, you would need 45 more degrees to fill up a 360. So this is exactly like the cotangent of 45 degrees in quadrant 4. Because 315 is in quadrant 4. If I've lost you, go back to starting to draw these angles. That's what we would get as the reference angle. This right here is your reference angle. What is the cotangent of 45 degrees? We look at that chart. That chart's going to be very helpful. Cotangent, 45 degrees. 1, and we're in quadrant 4, so is cotangent positive or negative? I heard both. It's negative. In quadrant 4, that's the C quadrant, so that's cosine and then secant that are positive. Yes?
How did you get the 315?
315, I did negative 45 plus 360. Same way from here, negative 405 plus 360 is negative 45, plus 360 is 315. This question specifically wanted me to have an angle between 0 and 360. What's up?
So if it's like a big angle like 315, again, can I just consider essentially the inverse of the one before, like the one right before we got a positive number as what I substituted?
Yeah. Yeah, yes.
How do you know what quadrant it's in?
That's a great question. You think about the quadrantial angles themselves. So this is 0, 90, 180, 270, and if I make it all the way around again, it's 360. So I have to know between which of these numbers it like falls in. 315 is between 270 and 360. So it's in quadrant 4.
Oh, okay.
Like when we were working with that 210 number, 210 is between 180 and 270, so it's here in quadrant 3.
Okay, yeah.
Does that make sense? Thank you for your questions. I love them. Last one for today. We're going to determine the angle measures with special reference angles. So we're going to find all the values of theta. If theta is in the interval between 0 and 360 degrees, and that the cosine of that angle is negative square root 2 over 2. First things first, let's make sure we understand the question. We want to know in one revolution of a circle, how many angles give us the value negative square root 2 over 2 when we take the cosine of that angle. So my output this time is an angle. I want to know what angles work. Couple things we want to think about. In the chart that you have that you've been looking at this whole time, was there an angle that was for cosine where you had square root 2 over 2?
I don't believe you had 45 degrees.
Yeah, the cosine of 45 degrees from your table is equal to positive square root 2 over 2. Now that's an interesting thing to note because we don't want a positive square root 2 over 2. We want the negative version of that. So it would be in different quadrants. Specifically, which two quadrants is cosine going to be negative? 2 and 4. So what we want is... Yep, that's what I meant. Thank you so much. What we want is the angles in those two quadrants that would use 45 as their reference angle. Meaning, if I had this angle here in quadrant 2, and this was 45 degrees, what is theta?
45.
Well, that's the reference. I want to know now what would be this angle if this much is 45 degrees. 135. What's 135 plus 45? 180. So what we found here is that in quadrant 2, then theta is equal to 135 degrees. There's one of the angles. Now, I know there's two answers to this question because we circled two quadrants in the ASTC diagram. So if I draw another one this time in quadrant 3, and remember my reference angle here is still 45 degrees, what is the full angle theta? 225. Very good. So that's 180 plus that 45 degree reference angle. Those are my two answers here.
Wait, 180 plus?
Say again?
180 plus?
180 plus because we're going beyond 180. Remember, the flat line is 180. Your negative x-axis is 180. In this question, we wanted less than that, so we subtracted from 180. In this one, we wanted more than that, so we added to 180.